Bismillahirrahmanirrahim. Sound waves. As we are familiar with sound in our daily life, so how the sound waves are produced. Like all type of waves, the sound waves are also produced by some oscillating source. The sound waves can travel through any medium and they cannot move without medium. So means that the sound waves are mechanical waves. As already we have discussed the types of the mechanical waves, that there are two types, the longitudinal waves and the transverse waves. So the sound waves in ear are longitudinal waves. That is, when sound waves travel through air or gases, so the particles of the medium oscillate parallel to the direction of propagation of the waves. So sound waves are mechanical waves and or longitudinal waves in gases. The sound waves, as we hear them, so we cannot hear all the sound waves. Our sensation of hearing can respond to a particular range of frequencies. That is, if the sound waves have frequency between 20 Hz and 20 kHz, we can hear them. So the audible frequency range for the sound waves is 20 kHz to from 20 Hz to 20 kHz. And there are now the sounds which have the frequency below the audible frequency range. That is, the sound waves whose frequency is below 20 Hz are said to be infrasonic waves, while the sound waves that have frequency higher than the audible sounds, that is, it means that the sounds having frequency greater than 20,000 Hz are said to be ultrasonic waves. So now what about the speed of the sound waves? Because already we have discussed the speed of a transverse wave, sinusoidal transverse wave on a stretched string. So what about the speed of a sound wave? So let us describe factorially the motion of one-dimensional longitudinal pulse moving through a long tube containing a compressible gas, and a piston at the left can be moved to the right to compress the gas and create a pulse like this. This is a gas-filled very long tube. It is a piston on the left end. So if we push this piston forward, it will compress the gas and that compression will travel through the tube. Similarly, if we start oscillating this piston sinusoidally, so periodically region of higher pressure, that is compressions, and low pressure, that is rarefaction, will be produced at this phase of the piston, and those compressions and rarefactions will travel through the air and the tube as a sound wave. So the compression region are denoted by more dark colors like this, and the rarefied regions are represented by light colors like this. So in this case we just consider a single pulse, that is, we push the piston once, that is compress the air in front of the piston, and leave it at that position. So what we see with time, that this compression moves along the tube to the right and leaving the area behind it as a rarefied region. So the regions through which the compression passes, the pressure over there increases and also the density of the gas increases. While the regions where a rarefaction exists, the pressure and the density of the gas decreases from its normal value or equilibrium value. So this is we consider the piston and the gas filled tube like this. We compress the air in front of the piston, and this produces a pulse, and that pulse moves to the right. Now we describe the motion of this pulse. So this pulse will move to the right with the speed of sound, and the speed of the compression towards the right will not be equal to the speed of the piston at which it was pushed. So the speed of the sound waves in air or in any gas can be written by the relation V is equal to B over rho, where B is the bulk modulus of the gas through which the sound wave is traveling, and rho is the density, the normal density of that gas. We will derive this relation later on. But if we compare this relation with the relation of the sinusoidal transverse traveling wave along a stretched string, that is V is equal to T over mu, so we see that there is a similarity between them. Here it is a bulk, this is a property which is an elastic property, and in the denominator there is an inertial property. Similarly, over here the tension is an elastic property and the mu is an inertial property again. So in general we can write that all the mechanical waves follow a general expression of the form V is equal to, that is the speed of the wave is equal to elastic property divided by some inertial property under the root. The speed of sound also depends on temperature of the medium. So with respect to temperature, we can write the relation for the sound waves through air like this: V is equal to 331 meter per second into 1 plus Tc. This is just Tc, not a double T. This is Tc. Tc means temperature in degree centigrade divided by 273 degrees centigrade. Where 331 meter per second is the speed of sound at 0 degree centigrade, and Tc is the temperature in degrees Celsius. This double T should not be taken. This is single T with a subscript C, that is means the temperature in degrees centigrade. An example: speed of sound in solid. So if a solid bar is struck at 1 inch with a hammer, a longitudinal pulse propagates down the bar with a speed V is equal to y over rho under the root, where y is the Young modulus of the material. Find the speed of sound in an aluminium bar. That is, हमारे पास एक एल्यूमिनियम बार है और एक एल्यूमिनियम रॉड है, और उसके एक सिरे को एक हैमर हथौड़े के साथ अगर मारा जाए तो उसके अंदर एक वेव प्रोपेगेट करता है, और उस वेव का स्पीड जो है वो y ओवर रो है. y क्या है? यंग मॉडुलस, एंड रो उसका डेंसिटी. तो अगर एल्यूमिनियम का बार है तो उसमें स्पीड ऑफ साउंड डिटरमिन करें. सो एल्यूमिनियम बार क्यों कहा जा रहा है कि उसके लिए आपने रो जो है वो किसी टेबल से उठानी है कि रो की वैल्यू एल्यूमिनियम के लिए क्या है और यंग मॉडुलस की वैल्यू क्या है. सो फॉर एल्यूमिनियम द यंग मॉडुलस इज दिस मच and the density is this. Thus, plug in the value in this general relation for the solids, you get that the value of sound, or the value of the wave pulse that is generated in this bar of the aluminium is 5.1 kilometer per second. This typical value for the speed of sound in solid is much greater than the speed of sound in gases, as we already discussed that at 0 degree centigrade the speed of sound in air is 331 meter per second, and this is 5 kilometer per second. That is mean 5,000 meter or 51,000 meter per second, while in air it is 331 meter just. So means it is in solid the speed of the wave is or the speed of the sound is about 17 times that of the speed of sound in air. Why it is so? Because the particles of the solids are very close to each other, so the wave can, any disturbance can move fastly through a denser material. This is the table from which we took the values of, which we can take the values of the speed of sound. So in gases, these are the gases in which the speed of sound is like this. These are the liquids at 25 degrees centigrade, then the solids, and here is an example. The speed of sound in a liquid. So apparently the speed of sound in liquid will be greater than the speed of sound in air, and will be less than the speed of sound in a solid. Let us check. Find the speed of sound in water, which has a bulk modulus of 2.1 into 10 to the power 9 Newton per square meter. This is B. And its density rho is 1 into 10 to the power 3 kilogram per meter cube, or 1000 kilogram per cubic meter. So we can easily find the speed of sound in water by the relation under the root B over rho, and that is equal to 1.4 kilometer per second. It comes to be 1400 kilometer per second, 1400 meter per second, sorry. So 1400 meter per second is much greater than 331 meter per second, and it is much lesser than 5100 meter per second, which was for the aluminium. Number B, the dolphin used this much this. So dolphin use sound waves to locate food. Experiments have shown that a dolphin can detect a 7.5 centimeter target 110 meter away. कि एक डॉल्फिन 7.5 सेंटीमीटर का कोई बॉडी वो 110 मीटर दूर से डिटेक्ट कर सकता है. even in murky water. For a bit of dinner, at that distance, how much time passes between the moment the dolphin emits a sound pulse and the moment the dolphin hears its reflection and thereby detects the destined target. So this is the information. The dolphin can detect 7.5 centimeter target at 110 meter. At this distance, that is, if a target is away 110 meter away, so how much time it takes for the dolphin to detect this target? Okay, that is, the dolphin will produce a sound pulse, and their sound pulse will be reflected from the target and the dolphin will hear it. So how much time it will take? So as we know, S is equal to Vt. This is general formula, that the distance is equal to the speed times speed multiplied by time. Acha. So here we know about the distance. Distance is given 110 meter. We know the speed of sound in water is this, and we have to determine the time. So time is equal to the distance divided by the speed. So now here you see that the distance is 220 meter, and here we have given the distance 110 meter. So this distance is traveled twice, because the wave produced by the dolphin will reach the target, reflected back, and reaches again to the target, to the dolphin. So the wave will have to cover twice this distance. So 2 times 110 gives you 220 meter divided by V. So this comes to be 0.16 second. In a very short time, the dolphin detects its target. Now, the periodic sound waves. Up till now we have discussed just a single pulse. The sound waves, apparently they are periodic waves, because a continuous wave should be produced by a continuous oscillation of some source. If that source oscillates periodically, so the wave it produces will be a periodic wave. So we again consider the same tube filled with gas and having a piston at the left end. So if that piston is oscillated sinusoidally, it will create regions of higher pressure, that is the compressions, and regions of low pressure, that is the rarefaction, and those compression and rarefactions will move like this. The compression and rarefaction will move to the right through the tube. This is the piston. It is moved into the tube, so it will produce a compression. When it is moved back, it will, like this, it will produce a rarefaction, a region of lower pressure. How much lower? Lower than the normal pressure region. So this piston oscillates. If we oscillate it like this, this is in this figure, it is moved forward from equilibrium position. Here it is moved backward. Again it is moved forward, backward, forward. So means that this piston oscillates like this. So if we oscillate it, so when it moves forward, to the right, it produces a compression. When it moves backward to the left like this, it produces a rarefaction. Again, to the forward, to the right side, it produces a compression, and when it is moved to the left, it produces a rarefaction, again a compression. So these compressions and rarefactions move along the tube to the right. In this figure, this is just one pulse that moves forward in this figure, and the piston is moved back, so a rarefaction along the compression is produced. Now again the piston is moved forward, so one compression was already produced, followed by this rarefaction, and again one compression, this one. And similarly we are producing again and again periodically compressions and rarefaction, and those compression and rarefactions will move through the gas to the right side. These will move with the speed of sound. Okay. So we can consider, as we have described already, the transverse waves along a string by a displacement y of xt is equal to ym sine of kx minus omega t. Those were sinusoidal waves, but the y was the transverse displacement. Here we can represent a sound wave by a wave function, the displacement wave function. That is the displacement of the particles from their equilibrium position. But now the particles displaced parallel to the direction of propagation of the wave. In the transverse waves, the particles were being displaced in a perpendicular direction through direction of propagation of the wave. That is the difference. So if we consider sound wave, represent the sound wave by a wave function of the displacement function, s of xt is equal to s maximum into cos kx minus omega t. Why we take here the function cos? Because look at this picture. When we compress the air, at this time we take the displacement is the displacement wave to represent the sound wave. So at time t is equal to 0, at the start the compression is maximum. When the compression is maximum, so the particles over here are displaced mostly, yani by maximum magnitude they are displaced at this position, and after a time period t by 2 they are displaced less, like this, from their equilibrium positions. So that's why we start with the cosine function. This is similar, this function is similar to that of the traveling transverse sinusoidal waves. Over there we took this y of xt is equal to ym, that is y maximum, into sine of kx minus omega t. Here it is to differentiate this displacement, this parallel displacement with the vertical displacement, we don't take it as y but take rather it as s, and s maximum is the maximum displacement of the medium from the equilibrium. In other words, the displacement amplitude of the wave. K is again the angular wave number and omega is the angular frequency of the piston. Similarly, we can also represent the sound wave produced in air by a pressure wave function like this, that is delta P is equal to delta P maximum into sine of kx minus omega t. And this displacement wave and pressure wave are 90 degree out of phase. The maximum the maximum value of the change in pressure can be shown to be rho v omega s maximum. We will find it very shortly, that this is equal to this. So now, how to derive this equation? Let us derive this delta P is equal to delta P maximum into sine of kx minus omega t. So let us come to its rigorous derivation. As we know from the definition of the bulk modulus, that the pressure variation in the gas is given by delta P is equal to minus V into delta V over V. We define the bulk modulus as minus delta P divided by delta V over V I. So we consider a small element of the thickness delta X of the gas in this tube. You can consider that, let us consider this compression only. So this compression will have a length delta X in this direction, this whole compression. And as it is a cylindrical tube, so we take its face area and this cross-sectional area throughout is uniform, we take it A. So the volume of this small element whose length is delta X will be equal to delta X multiplied by the cross-sectional area. So the volume VI will be A delta X. And if this compression arrives here or rarefaction arrives here, so the volume of this area may change. The volume of this element may change. If compression arrives here, so the volume will decrease. If rarefaction passes through it, so its volume will increase. By passing the compression, the volume decreases. When rarefaction passes through some region, so its volume, a particular amount of the gas will increase. So we take the change in volume as delta V. So but that delta V is not equal to A delta X. A delta X is the original volume, the undisturbed volume when the wave does not pass, or it is the equilibrium volume of some element of length delta X. Now when, let's suppose, a compression passes through it, so its volume will decrease. Yani this A delta X, the matter, the gas that occupied A delta X will now occupy a smaller volume. And what will be the change of the volume? That we can write as A delta S, where delta S is the change in the displacement function. So we can write delta P is equal to minus B delta V over VI, this one, and for delta V we write A delta S, and for VI we write A delta X. So this will be minus B delta S over delta X. A will be cancelled out, and if we take a very thin volume element, that is if we decrease delta X to an infinitesimal value, that is if delta X tends to 0, so this delta S over delta X will give us the derivative of S with respect to X, that is partial S over partial X. This partial S over partial S, because S is a function of position and time both. So if we only take the derivative with respect to x, that will be partial derivative. So we can write delta p is equal to minus v curly s over curly x, the partial derivative of the displacement function or the wave function with respect to x. Now we have already seen that this s is s maximum into cos of kx minus omega t. So if we differentiate it with respect to x, we get bk s maximum to sine of kx minus omega t. Now, as from the first equation we know that b is equal to rho v square, so if we plug in that value, we get delta p is equal to rho v square k s maximum into sine of kx minus omega t, and using the value of k is equal to omega over v, we can get delta p is equal to rho v omega s maximum into sine of kx minus omega t. So what is this now? This thing rho v omega and s maximum is actually delta p maximum, and thus we arrive at the result delta p is equal to delta p maximum into sine of kx minus omega t. So this is the pressure variation sinusoidally. This represents the pressure variation at position x and time t, and is a sinusoidal function that represents a sound wave as a pressure wave.